Okay, here is section 5. We're going to build off of some of the stuff we did in 2 because obviously we're coming back to graphing. And we talked a lot about graphing in section 2. That was the focus. A few other things on the topic for this lesson. Not many, to be honest with you. It's fairly short. Anytime we go back into graphing, I like to throw out the reminder that what we're doing is creating a visual representation of all of our solution points. Far too often when we do graphing, I feel like there's a disconnect between an equation of a function and its graph. And it's kind of lost that the two mean the same thing. One of them is just putting it in what we would call symbolic form, where you're just working with the numbers, and the graph is a visual representation that kind of shows you the pattern of how these solution points are all related. Okay, that is what graphing is all about. Oh, let's head up here. I don't want to talk about zeros yet. Domain and range is what I want to talk about now. Your possible x values and your possible y values. If you have something like the line that we see on the graph to the left here, it's got arrows on both sides, and that arrow is going to continue to go farther and farther to the left and farther to the right, which just means that for our domain, x can be any real number. There's no restrictions on it. And now I go to the y values and I start to think vertically. Is there anything that's going to stop this function from getting bigger and bigger and bigger in terms of its y values, or smaller in terms of its y values? And the answer is no. And it's all real numbers. Now, if you have a line, other than a couple exceptions with like a constant function or like a vertical line, those cases we looked at where the slope was like 0 or undefined, you're going to see this happen with a line. It's not going to have any restrictions. Okay. Now we have a curve over here on the left, or on the right. Looks like maybe could be part of a cubic graph, perhaps. Hard to tell. It doesn't have the arrows, and it's got these stopping points to the left and to the right, and up and down. Okay. A lot of the functions that we work with, particularly in application settings, will have some kind of restriction on their domain. Okay. If there's a restriction on the range, and you'll see this all throughout the problems we do with graphing, it's tricky to talk about restrictions to range without a graph. You can do it, okay? You have to be able to look at the equation that you have, and you have to know so much stuff about that type of function if you want to discuss range without a graph. So for our class, I just don't do it. If I'm going to ask you about range, you're going to have a graph so you can look at it and visualize the points. Now back to the domain here, I'm looking left to right. And I look over to the left and I see this point where the graph stops, and I see that that's at -4, and it never goes to the left. And then I look over to the right, and I can see it goes all the way over to 7. So with the restrictions I have here, x can be between -4, and notice I included it because the circle was shaded, and then I went all the way over to 7. That's the biggest it could possibly be, sort of, because it doesn't actually include 7. It could approach 7, so 6.9 could be in my domain, 6.99, 6.999999. Okay, throw on as many 9s as you want, and you're still in the domain, but once I jump to 7, I'm now saying that I'm out. Range, we do the exact same thing, except now I'm looking at it vertically. So I'm looking at y values, and I can see down here at the bottom, heads all the way down to -3. And then at the point up at the top, it goes as high as 6. Now both of those circles were shaded in, so I'm including those. Okay, there's solution points at each of those, so -3 and 6. Those should both be included. All right, let's talk about zeros. I'll give you 2 of them here. The first thing I want to make clear, because this kind of thing happens, where you can have a question that seems confusing, and really all it's about is the terminology that was used. Again, when we talked about graphing in section 2, we looked at how to find x-intercepts and y-intercepts as reference points. If we're putting together a graph, those points are helpful to kind of visualize what this graph is doing. In section 5, all of a sudden we get this question about, find the zeros of a function. So the first thing I want to do here is to make it really clear that finding zeros and finding x-intercepts is the exact same thing. Okay, saying find the zeros is just like a shorter, easier way to say it. Okay, now if you look back to your notes from section 2, you'll see that under finding x-intercepts we said set the function equal to 0 and solve. Okay, because you set it equal to 0, that's where it takes the name of zeros. So I have f of x equals, let's do x squared plus x minus 10. Okay. I'm going to drop down to the bottom. Give myself a little space here. One method that we can use to solve a quadratic is to factor it, which you'll see some quadratics. You could even see one like this on a test. We really don't dive into really deep into quadratics until chapter 2. So if I give you one that's got some factoring, I'm going to keep it pretty modest, and one that splits up into 2 linear factors pretty well. I need 2 factors of -10, but I need them to work in such a way that if I were to FOIL, that I get back to 1 for the middle term. If I do -5 here and +2, and trial and error would be a good way to go with this one, just because -10 doesn't have that many factors. You're either looking at some combination of ±1 or ±10, or ±2, ±5. Okay, which gives you really at most 4 possible cases to check, which is not, that's what I mean when I leave the factoring pretty light. I'm going to give you ones where you can do it that way. There are better ways to do it, but we'll do it that way for now, just to keep it simple, because I don't really want to get too much into factoring yet. Once we do that, what it sets us up for is we could take both of these factors and we can solve them separately. If I add 5 and divide by 3, 5/3 is 1, and then x equals -2 would be the other. Okay. Now there's a lot more characteristics that we'll get into, and you might actually be thinking to yourself, I could look at that quadratic and I could actually tell you where the vertex is. We haven't even talked about that term, vertex. I know that it opens up, right? This is all stuff that we'll get into, but this is part of it. 5/3 is right between 1 and 2. Okay? Even if you didn't know anything else about that quadratic graph, those 2 points at -2 and 5/3, this graph has to cross through both of those points. Now let's hop over here. Let's do another one. Let's do a rational function. We haven't really talked about those, but I want to actually throw one a type of function we haven't really talked about much, because sometimes those trick you into thinking, oh my goodness, this one's different. It's got to be different, right? Well, that's really what I'm trying to get at on this slide, is if you're finding zeros. No, it's not. Okay? It's always going to be set the entire function equal to 0. And then we need to solve. Okay? The manner in which we go about solving may change a little bit. Like this one we're not going to factor. I'd multiply both sides by t plus 5, which actually works out great, because it just goes away and you have 2t minus 3, which would follow that 3 is equal to 2t. And finish that t is 3 over 2, which is 1.5. And here's one where I'm not even going to get into other characteristics of this graph, because we don't know them yet. You maybe remember a little bit from functions class last year. Maybe. I would guess that you don't. But right there at 1.5, we know this graph crosses through that point. What else it's doing, who knows? We'll get to that later, but we know it goes through that point. All right, increasing and decreasing. That's something that comes up a lot with functions, is we like to know and be able to communicate when a function is increasing and when it's decreasing. Okay? Let's start with increasing, and we typically communicate it in terms of x values. Okay? Now, a nice way to do it is just kind of trace over the function. All right? And at first it's increasing till we get there. So then what I look for is what x value is that at. Looks like 0. So I'm going to say here that if x is less than 0, I've got a graph here that is increasing. Okay? Now we're not going to talk as much about this yet. This one makes it more obvious, so I'm going to say it. A cubic curve like we have in the second example isn't quite as obvious. That we have points where the graph is constant, or it's not going up and it's not going down. This one's a little bit different because there's not just points where it's not increasing or decreasing, there's an interval. And you're typically looking, if you have something like a horizontal line, which this one does, and for the x values, it's between 0 and 2. So there I'd have to specify that if I've got this interval of values that, you know, the increasing or decreasing thing, that's not happening. It's just, it's not going up, it's not going down. And then you can see after 2, it starts to decrease, so then I would just say when x is greater than 2. So that's a good example to have because it shows you all three possibilities of what's happening. Now this one I'm going to adjust it a little bit. I'm only going to talk about increasing and decreasing. Now technically there are 2 points on the graph where it's a constant, where it's not increasing or decreasing. But the difference is they're points, not an interval. Okay? It looks as though things change at these 2 points. Okay? And the only place where it's decreasing is in between those. So here I'm going to say in between -1 and 1. I didn't include them. Okay, at this point in the semester, if you did include -1 and 1, I wouldn't be too worried about it. I mean, technically you shouldn't. But that's the whole deal with the function being a constant, where it's not increasing or decreasing. That minimum and maximum point, technically that's what's happening, is this graph starts increasing and then it gets to x equals -1, which is right here. And for that one single point, it's stationary or constant, and then it starts to decrease. Now for increasing, I have two separate intervals, and as a result, I have to state them separately. You've got one here, and then you get to -1, and it does its little decreasing thing, and then it picks up here again and increases. But it is two separate intervals, so I have to say it was two separate inequalities. It's increasing when x is less than -1 and when x is greater than 1. Okay? It was that interval in between, that's where it was decreasing. Okay? And notice on this one, I didn't bother talking about the constant points. We'll get there. You know, it's kind of getting into a little bit of a calculus topic as to, in the very next slide, we're going to start to talk about secant lines. But as far as that type of stuff, there's some interesting things going on at those 2 points, that max and minimum where the function changes direction. All right, this is the exact same function that you were looking at, still just a little cubic. Here's what I want to do. First of all, just talk through secant lines. Gets into a big topic, a big calculus topic of measuring the slope of a curve, which is trickier to do because it's not like a line where the slope is a constant. What characterizes a curve is that the slope is constantly changing, depending on where you're at. So there's this whole element, you know, if you want to talk about the slope on a curve, where are you on the curve? Okay? A great place to start is to talk about a secant line that will give you an average rate of change. The first one we're going to do on this graph is I want the average rate of change from x equals -2 to x equals 0. Now right here is -2, -2, and this function does go through the point 0, 0. Okay, this point right here, by the way, is 1, -2, and over here we have -1, -2. All right, now I have those 2 points, and I draw in my secant line. Now that's an average. There's a lot going on with this graph between -2 and 0. It starts to increase pretty quickly, and then it levels off and it comes back down, so it does some increasing, some decreasing. Now the 2 points that I picked, I drew in the secant line, and I see that it's positive, which tells me for this interval it did a little more increasing than decreasing, because overall that's what the secant line is going to tell me, the average rate of change. The big thing you have to keep in mind here, I've got these 2 points that form my secant line. Slope is slope, no matter how you look at it. Slope of a line. You need 2 points, change in y over change in x. A secant line is absolutely no different. Okay? So once I identify the 2 points that I'm going to use to form my secant line, it's a slope calculation like you've done who knows how many times over the years. Okay? It's just a matter of identifying the 2 points that you need to use. Okay? The slope of that secant line is 1. Okay? So between -2 and 0, that was the average rate of change that we saw, 1. Oh, let's do one more. Let's do another secant line, but let's look at the average rate of change from 0 up to 1. So that would be here to here. I'll draw that secant line in red. A couple things to notice. Number one, this one's got a negative slope, which if you think about this, when we were talking increasing and decreasing, we had said for this graph it decreases between -1 and 1. Okay? Well, we're 0 to 1. We are in part of that interval where this graph is decreasing. So I am totally expecting to get a slope for this secant line that's negative. This way, in this interval, it doesn't change directions. So my secant line was pretty close to the curve. And part of what's going on there is, notice the 2 points I picked for part B are closer together. In part A, they were 2 units apart, and here they're only 1. As far as what's actually going on with the slope, if you pick 2 points to make a secant line that are closer together, it gives you a more accurate kind of an estimate. It's really an average, but it's kind of like an estimate of what's going on with the slope. So here, between 0 and 1, my slope of my secant line is going to tell me pretty closely what's going on as far as the slope between these 2 points. But again, it's slope. I've got my 2 points. Okay, 0 minus -2. Right, I'm using this point, and I'm using that one. 0 minus -2 over 0 minus 1. Okay, I just need the 2 endpoints that are forming the 2 points that I picked that are forming my secant line. You get 2 over -1. And we get a slope of -2. Right on what we expected. Negative. A little bit steeper than the first one that just had a slope of 1, but we definitely see that negative slope going on there.